14.46 billion years, that was the number. Written plainly in the data, confirmed and reconfirmed across months of painstaking analysis, and yet impossible. Because in 2013, when Howard Bond of the Space Telescope Science Institute in Baltimore finally published his team's findings, the universe itself was understood to be only 13.8 billion years old. The cosmic microwave background, that faint glow of ancient light still washing across the sky from the moment matter first cooled enough to release photons, had been mapped with exquisite precision by satellite observatories. The age it yielded was solid. It was foundational. It was the number upon which all of modern cosmology rested. And here was a star that appeared to be older than everything. Not by a little. Not by some marginal discrepancy that could be waved away as rounding error or instrumental noise. The central estimate placed HD's Sostorno 283 at more than 500 million years older than the Big Bang itself, even accounting for the measurement's uncertainty, plus or minus 800 million years, a range that technically allowed the star to be as young as 13.66 billion years. The situation remained deeply uncomfortable. The best value, the most likely value according to the mathematics of observation and inference, suggested that this dim point of light in the constellation Libra had somehow been burning before there was a universe for it to burn in. Howard Bond understood exactly what he was presenting. He had spent years refining the measurement, pushing the precision of every input variable as far as current technology would allow. When he spoke to the press, he framed the paradox with the directness of someone who had already spent countless hours wrestling with it in private. Put all of those ingredients together, he said, and you get an age of 14.5 billion years, with a residual uncertainty that makes the star's age compatible with the age of the universe. Compatible, but only just, and only if you were willing to live at the outer edge of the error bars. The central value still pointed somewhere it had no right to point. Maybe the cosmology is wrong, Bond offered, stellar physics is wrong, or the star's distance is wrong. 3 possibilities, each of them, in its own way, a kind of vertigo. If the cosmology was wrong, if the universe was actually older than the cosmic microwave background suggested, then the entire framework of Big Bang cosmology would need revision. The expansion rate of space, the density of dark energy, the formation timeline of the first galaxies, all of it would shift. Textbooks would need rewriting. Decades of observation and theory, brought into coherence with painstaking effort, would suddenly contain a crack that might widen into a chasm. If stellar physics was wrong, if the models that predicted how stars aged, how they brightened and cooled and consumed their fuel, then every age estimate for every ancient star in the galaxy became suspect. The chronology of the Milky Way's formation, the timeline of chemical enrichment that built the heavy elements in your bones and mine, the careful reconstruction of 12 billion years of galactic history, all of it rested on the same theoretical scaffolding. A flaw deep enough to explain HD Arsensis 83 would ripple outward through everything. And if the distance was wrong, well, distance in astronomy is where measurement meets philosophy. A star's intrinsic brightness cannot be known directly. We see only how bright it appears from Earth, and we must infer how luminous it truly is based on how far away it lies. Get the distance wrong, and you get the luminosity wrong. Get the luminosity wrong, and you misplace the star on the Hertzsprung-Russell diagram. Misplace it there, and every conclusion about its mass, its evolutionary state and its age becomes corrupted at the root. In 2013, Bond's team had used the fine guidance sensors of the Hubble Space Telescope, some of the most precise astrometric instruments ever built, to pin down HD to 2/8 distance through parallax. This was not a casual measurement. This was the gold standard, the method that astronomers had trusted for over a century to anchor the distance scale of the cosmos. They had done everything right, and still the number came out wrong, or perhaps. And this was the thought that kept certain astronomers awake at night. Perhaps the number came out exactly right, and it was our understanding of rightness that needed to change. This documentary is an attempt to follow that question wherever it leads. Over the next 2 hours, we will trace the history of a single star, where it came from, how it was found, what its light reveals about conditions in the universe before Earth existed, before the Sun existed, before most of the stars you can see on a clear night had even begun to form. We will examine parallax measurements made by satellites orbiting the Earth, and stellar evolution models refined over decades of theoretical work. We will meet the astronomers who have devoted careers to understanding objects like HD 2043, objects that seem to remember a cosmos younger than themselves, and we will sit with the discomfort of not knowing. Because in science, the most interesting moments are rarely the ones where everything fits together. They are the moments where something refuses to fit, where a single stubborn data point forces the entire edifice to pause and reconsider. HD 2043 is that kind of object. It is a splinter in the eye of cosmology. It is the star that broke the calendar, and it is right there in the night sky, visible with a pair of binoculars if you know where to look. Libra is not a constellation that draws the eye. It lacks the drama of Orion, the sweep of Scorpius, the ancient familiarity of the Big Dipper. It sits in a quiet stretch of the zodiac, south of Virgo and west of Scorpius, and its stars are modest. None brighter than third magnitude, most fainter still. To modern observers, Libra is a footnote, a place the ecliptic happens to pass through on its way to more interesting territory. But if you train a pair of binoculars on the right patch of that dim constellation, roughly 7 degrees southeast of the bright star Zubenelgenubi, the southern claw, you can find something extraordinary. It is a point of light with an apparent magnitude of 7.205, which means it hovers just below the threshold of naked eye visibility. On a truly dark night, with perfect conditions and well-adapted eyes, some observers claim to glimpse it without optical aid. For most of us, though, it requires at least binoculars, a small brightening in a field of dim companions, indistinguishable at first glance from thousands of other such stars. This is HD 14283. This is Methuselah. The name is not official. The International Astronomical Union, which governs such things, still lists it only by its catalogue number, a designation inherited from the Henry Draper catalogue, that monumental spectroscopic survey published between 1918 and 1924. HD 14283 is one of nearly 400,000 stars recorded in that effort, each assigned a number in rough order of position across the sky. But among astronomers who study the ancient universe, the nickname has stuck. Methuselah, the oldest man in the Hebrew Bible, who lived 969 years before the flood. It is a fitting name for a star that seems to have outlived the universe that contains it. What first drew attention to HD 14283 was not its age, that would come much later, but its motion. Most stars appear fixed against the background of more distant stars. This is an illusion born of scale. Stars are moving, often at tremendous speeds, but they are so far away that their apparent positions shift only imperceptibly over human lifetimes. The stars of Orion's belt, the stars of the Southern Cross, will look essentially the same to observers 1,000 years from now as they do tonight. Proper motion, the angular shift of a star's position across the sky, measured in arc-seconds per year, is typically tiny. A star moving at 1 arc-second per year would take 3,600 years to drift the width of a full moon. HD 14283 moves at roughly 1.1 arc-seconds per year in right ascension and 0.3 arc-seconds per year in declination. Combined, its total proper motion approaches 1.15 arc-seconds annually, which may sound small, but places it among the fastest moving stars visible from Earth. At this rate, it crosses the width of a full moon in roughly 1,500 years. For an object 200 light-years distant, that angular speed translates to a tangential velocity of approximately 335 kilometers per second relative to the Sun. This is not a star drifting gently through the neighborhood. This is a star in a hurry, falling through the galactic disk on an orbit that carries it up and out of the plane most stars call home. By the early 20th century, when astronomers first began systematically cataloguing high-velocity stars, HD 14283 stood out. Its speed was anomalous. Stars born in the disk of the Milky Way tend to move in roughly circular orbits, like horses on a carousel, keeping pace with the general rotation of the galaxy. Their velocities relative to the Sun are modest, a few tens of kilometers per second at most. But here was a star moving at hundreds of kilometers per second, and in a direction that suggested it was not part of the carousel at all. In 1912, Walter S. Adams, one of the great spectroscopists of his era, working at Mount Wilson Observatory in California, flagged HD 13283 as a high-velocity object worthy of further study. Spectroscopy at the time was still a young art, but Adams could already see hints that this star's light was peculiar. The absorption lines in its spectrum, those dark gaps where atoms in the star's atmosphere swallow specific wavelengths of light, looked different from what he saw in the Sun. The patterns were subtly wrong, as if certain elements were missing or dramatically depleted. It would take nearly 4 decades before anyone fully understood what those missing lines meant. In 1951, Joseph W. Chamberlain and Lawrence Aller published an analysis that would reshape how astronomers understood the history of the Milky Way. Working with spectra of HD 14283 and a handful of similar high-velocity stars, they demonstrated that these objects were profoundly metal-poor. In astronomical parlance, metals refers to any element heavier than helium, everything from lithium to uranium, the entire periodic table beyond the 2 simplest atoms. The Sun contains about 1.8% metals by mass, a heritage of nearly 9 billion years of stellar nucleosynthesis in earlier generations of stars. Heavy elements are forged in stellar cores and scattered by supernova explosions. Each generation of stars inherits the enriched debris of those that came before. But HD 1402283 was different. Its metal content was roughly 1,000th of the Sun's. It was almost pure hydrogen and helium, with only trace contamination from heavier elements. It was, in other words, cosmologically primitive, a star that must have formed before the galaxy had time to build up its reserves of iron and oxygen and carbon. Chamberlain and Aller's discovery helped establish the distinction between population 1 and population 2 stars, a classification system that remains fundamental to galactic archaeology. Population 1 stars, like the Sun, are metal-rich, relatively young, and found in the thin disk of the Milky Way. Population 2 stars are ancient, metal-poor, and typically found in the galactic halo, that vast diffuse sphere of old stars surrounding the disk, remnants of the galaxy's earliest epochs. HD 14283, with its high velocity and low metallicity, was a textbook population 2 star. It was a halo interloper, passing through the solar neighbourhood on an orbit that carried it far above and below the galactic plane. By mid-century, HD 14283 had become a benchmark object, a reference point for studies of metal-poor stars, a test case for theories of stellar evolution and galactic formation. Generations of astronomers returned to it again and again, refining measurements of its spectrum, its velocity, its distance. It was not the only ancient star known, but it was one of the most accessible, close enough to study in detail, bright enough to observe with relatively modest instruments, and extreme enough in its properties to reward investigation. What no one yet understood, what would not become clear for another half-century, was just how extreme those properties were. Because the very characteristics that made HD 14283 a useful benchmark also made it a time bomb. Every improvement in measurement precision brought its apparent age closer to an impossible value. And in 2013, when Howard Bond's team finally pushed the parallax measurement to Hubble-level accuracy, the bomb went off. To understand why HD 14283's age is so troubling, you must first understand how astronomers read the ages of stars. The method is elegant in principle, fiendishly difficult in practice, and it rests on a diagram that has shaped a century of astrophysics. The Hertzsprung-Russell diagram, or HR diagram as it is usually called, was developed independently in the early 1900s by Einar Hertzsprung in Denmark and Henry Norris Russell in the United States. It is in essence a scatter plot. On one axis, you place a star's temperature, or its spectral type, which amounts to the same thing. On the other axis, you place its intrinsic brightness, absolute magnitude corrected for distance. When you plot a large sample of stars this way, a striking pattern emerges. Most stars fall along a curving band that stretches diagonally across the diagram, from hot, luminous blue stars in the upper left to cool, dim red stars in the lower right. This band is called the main sequence, and it represents stars in the prime of their lives, stars that are generating energy by fusing hydrogen into helium in their cores. The Sun is a main sequence star. So are the majority of stars you can see in the night sky. The main sequence is where stars spend most of their existence, burning steadily through their fuel supply over timescales measured in millions or billions of years. But hydrogen does not last forever. Eventually, the core exhausts its supply. What happens next depends on the star's mass, but for stars roughly similar to the Sun, the pattern is predictable. As the core runs out of hydrogen, it contracts and heats up. The hydrogen-burning region migrates outward, forming a shell around the inert helium core. The star's outer layers expand and cool, and its luminosity increases. On the HR diagram, the star moves off the main sequence. It drifts upward, brighter, and rightward, cooler, heading toward the region occupied by red giants. This transition, from main sequence to subgiant to red giant, follows a well-defined track, and the speed at which a star traverses it depends almost entirely on its mass. Massive stars burn hot and fast. They leave the main sequence in a few million years. Low-mass stars burn cool and slow. They can remain on the main sequence for tens of billions of years. A star's position on the HR diagram, combined with a good estimate of its mass, thus encodes information about its age. This is where isochrones enter the picture. An isochrone is a theoretical curve on the HR diagram representing stars of a single age but varying masses. Stellar evolution models, complex simulations that track how stars change over time, accounting for nuclear reaction rates, opacity, convection, and a host of other factors, can generate isochrones for any specified age. A 10 billion year isochrone shows where stars of various masses should appear after 10 billion years of evolution. A 12 billion year isochrone shows the same thing 2 billion years later. By overlaying a star's observed position on a grid of isochrones, astronomers can read its age, at least in principle. In practice, everything depends on precision. To place a star accurately on the HR diagram, you need two things: its temperature, which can be derived from its spectrum, and its absolute magnitude, which requires knowing both its apparent brightness and its distance. Temperature is relatively straightforward. Distance is not. This is where parallax comes in, and why the 2013 measurement mattered so much. Parallax is the apparent shift in a star's position caused by Earth's motion around the Sun. Over the course of a year, a nearby star traces a tiny ellipse against the background of more distant stars. The size of that ellipse, measured in arcseconds, is inversely proportional to the star's distance in parsecs. A star at 1 parsec would show a parallax of 1 arcsecond. A star at 10 parsecs would show a parallax of 0.1 arcsecond. HD Waldontoldon 3 lies at roughly 62 parsecs, about 200 light-years. Its parallax is therefore something like 16 milliseconds, 16 thousandths of a second of arc, an angle so small that resolving it requires extraordinary precision. Ground-based telescopes struggle with such measurements. The atmosphere blurs images in ways that mask tiny shifts. Space-based observatories fare better, free from atmospheric distortion, able to track stellar positions with unprecedented accuracy. The European Space Agency's Hipparcos satellite, which operated from 1989 to 1993, revolutionized parallax astronomy. It measured the positions and motions of over 100,000 stars with millisecond precision, providing distance estimates that were an order of magnitude better than anything previously available. HD Polostas 83 was among the stars Hipparcos observed, and the resulting distance estimate, combined with the star's known spectral properties, placed its age at approximately 16 billion years, 16 billion years, in a universe only 13.8 billion years old. For over a decade, that number sat uneasily in the literature. Some astronomers treated it as a statistical outlier, likely to resolve with better data. Others noted the uncertainties in stellar evolution models and suggested that improved physics might bring the age down. A few pointed out that even the cosmic microwave background measurements had their own uncertainties, and that perhaps the universe was older than claimed. What Howard Bond's team did in 2013 was push the parallax to a new level of precision. Using the fine guidance sensors on Hubble, instruments designed primarily for pointing the telescope but capable of astonishing astrometric accuracy, they measured HD 283's position over hundreds of observations spanning several years. The resulting parallax was the most precise ever obtained for this star, and it placed the distance at approximately 190 light-years. The new distance was slightly closer than earlier estimates had suggested. This meant the star was slightly less luminous than previously thought, which meant it sat slightly lower on the HR diagram, and that in turn meant it was slightly younger. The age dropped from 16 billion years to 14.46 billion years, still impossibly old, but less impossibly old. The uncertainty of 800 million years meant that the very youngest end of the error bars, 13.66 billion years, was technically consistent with the age of the universe. Technically consistent, but just barely. And the central value, the most likely value given all the data, still pointed past the Big Bang into a time that could not have existed. HD 140283 is classified as a yellow subgiant of spectral type G0IV-VM5. That cumbersome string of letters and numbers encodes everything astronomers know about its light. G0 places it close to the Sun in temperature, a little hotter, a little bluer, but broadly similar. IFEF indicates that it sits on the boundary between the main sequence and the subgiant branch. No longer a core hydrogen burner, not yet a red giant, but something in between. The M5 suffix flags its extreme metal deficiency. This position, poised exactly at the main sequence turnoff, the precise moment when a star begins its final evolutionary transformation, is both a blessing and a curse. It is a blessing because the turnoff is the most sensitive part of the HR diagram for age determination. Stars spend millions or billions of years on the main sequence, drifting imperceptibly brighter and cooler, but the turnoff itself happens relatively quickly. A star's luminosity and temperature at this moment encode its age with maximal precision. If you can catch a star at the turnoff, you can read its clock. But it is a curse because the turnoff is also where stellar evolution models are most sensitive to their inputs. The rate at which a star crosses from main sequence to subgiant depends on subtle details of physics: the opacity of its interior, the efficiency of convective mixing, the precise nuclear reaction rates that govern hydrogen fusion. Change any of these parameters by a small amount, and the predicted age shifts. Metallicity matters too. Metal-poor stars evolve differently than metal-rich ones, and the theoretical isochrones must account for this. Even the star's initial helium content affects the calculation, and that is something we cannot directly observe. HD 140283's mass is estimated at roughly 0.81 solar masses. Modest, but not unusual. A star of this mass, born in the early universe with minimal heavy elements, would have burned through its core hydrogen over roughly 12 to 14 billion years. The models, when tuned to the observed temperature, luminosity and metallicity, yield an age that clusters stubbornly around 14 billion years or a bit more. The Hubble measurement in 2013 was not the final word. Science rarely offers final words, only best current estimates subject to revision as new data arrive. In 2021, a team using the Scherer interferometer, an array of optical telescopes in California capable of resolving stellar surfaces, reported a new analysis. By directly measuring HD 283's angular diameter, they could derive its radius independently of parallax. Combined with updated stellar models, this yielded an age of 12.01 billion years, with an uncertainty of only 50 million years, 12 billion years, comfortably younger than the universe. The star, it seemed, had finally been brought to heel. But the Cara result carried its own assumptions, its own model dependencies. Not everyone was convinced. The tension had lessened, but it had not disappeared. And the history of HD 140283, the way its measured age had drifted over decades, sometimes dropping toward consistency with cosmology, sometimes rising back toward impossibility, suggested that the final answer was not yet in. What we know for certain is this: HD 140283 is extraordinarily old. Whether its true age is 12 billion years or 14 billion years or something in between, it formed in an epoch that modern humans can barely conceptualize. When HD 140283 ignited, the Milky Way was not yet fully assembled. The heavy elements that would one day form Earth did not yet exist. The galaxy was a smaller, wilder place, a swarm of proto-galactic fragments still merging and colliding, threading streams of ancient stars into what would eventually become the spiral disk we see today. HD 140283 fell inward from somewhere out there, from the primordial halo, from that ancient spherical cloud of first-generation stars that still surrounds the disk. Its high velocity is not random. It is a memory of where it came from, a trace of an orbit that carries it up out of the plane of the Milky Way and back down again in a great looping arc that takes hundreds of millions of years to complete. Right now, it happens to be passing through our neighbourhood, close enough to study in detail. In another million years it will have drifted away, receding into the halo once more. We are fortunate to live at a moment when this traveller is nearby. We are fortunate that our technology has advanced just far enough to measure its parallax, to pass its spectrum, to place it on the HR diagram and read the clock encoded in its light. And we are fortunate, if that is the right word, that the clock reads a time we do not fully understand, because that is what HD Stoltondoro 283 offers us. Not certainty, but a question. Not an answer, but a tension that refuses to dissolve. Either our models of stellar evolution are subtly wrong, and stars age differently than we think, or our measurements of the cosmic microwave background are subtly wrong, and the universe is older than we believe, or both are right within their uncertainties, and HD 140283 simply formed in the very first moments after the Big Bang, a relic of an era when the cosmos was still opaque with plasma, when the first atoms were just beginning to fall together under gravity, when stars like this one were the only light there was. Methuselah, the star that remembers a time before there was time, the star that broke the calendar, and it is right there, in Libra, waiting for anyone with a pair of binoculars and the patience to find it. A 7th magnitude point of light, crossing the sky at 1,000 kilometers every 3 seconds, older than anything else you will ever see with your own eyes. It does not know it is impossible. It simply burns, as it has burned for longer than the Earth has existed, carrying its paradox silently through the dark. The paradox, though, does not rest on a single measurement. Even if we set aside the parallax entirely, even if we grant that the distance to HD 1+2 might still carry some residual uncertainty, some systematic error yet to be discovered, there is another line of evidence, one that does not depend on geometry at all, one that is written into the star itself, atom by atom, in the very composition of its light. When astronomers spread that light into a spectrum, they find something remarkable. The dark lines that should appear where iron absorbs specific wavelengths of light are almost absent. Not quite invisible, HD 140283 is not a true first-generation star, not one of the primordial giants that formed from pure hydrogen and helium in the absolute beginning. But it is close. Its iron abundance, measured against the Sun's, comes in at roughly 1 part in 200. Some measurements place it even lower, at 1 part in 250. The notation astronomers use is FVH, Qua 2.4, give or take 1/10 of a dex. That negative number means HD Stoltondoro 283 carries approximately 0.04% of the iron the Sun possesses. It is by any standard extraordinarily metal poor, and that poverty is not incidental. It is a signature, a timestamp more fundamental than any parallax measurement, because it is rooted not in geometry but in nuclear physics. Consider what iron is and where it comes from. In the language of astronomy, metals means everything heavier than helium, a usage that would baffle any chemist but makes perfect sense when you understand what the universe was made of at the beginning. When the Big Bang nuclear synthesis ended, roughly 3 minutes after the initial expansion, the cosmos contained hydrogen, helium, and trace amounts of lithium. That was all. No carbon, no oxygen. No silicon, no calcium, no iron. The periodic table stopped at element 3. Everything else had to be manufactured later, inside stars. The cores of massive stars fuse hydrogen into helium, helium into carbon, carbon into oxygen, and so on up the chain, each successive reaction requiring higher temperatures and pressures, each one building heavier nuclei until the sequence terminates at iron. Iron is the end of the line for fusion. Beyond it, the reactions consume energy rather than release it, and the star's core can no longer support itself against gravity. The result is collapse, and then explosion. A supernova that scatters the freshly forged elements into the surrounding gas, seeding the next generation of stars with metals. This is the cycle of stellar nucleosynthesis, and it takes time. Each generation of massive stars must live out its brief, violent life, a few million years at most, before it can contribute its metals to the interstellar medium. Each new generation of stars forms from gas that is slightly richer in heavy elements than the generation before. The Sun, born roughly 4.5 billion years ago, inherited the accumulated metals of billions of years of prior stellar evolution. Its iron abundance reflects all those generations of supernovae, all those cycles of enrichment. HD 1483 did not inherit that legacy. It formed from gas that had barely been touched by stellar nucleosynthesis. 1 or 2 generations of supernovae, perhaps, had scattered their ashes into the primordial cloud from which it condensed. Enough to explain the trace of iron it carries, but only barely. The star's extreme metal poverty means it must have formed very early, before the galaxy had time to build up the chemical reservoir that later stars would draw upon. This is not speculation. It is a direct consequence of the physics. If HD 148283 had formed recently, it would have formed from gas that was rich in metals. There is no metal-poor gas left in the disk of the Milky Way. The interstellar medium in our neighbourhood has been recycled through so many generations of stars that it now carries roughly the same iron abundance as the Sun. Any star forming today, in the disk, would inherit that abundance. HD 148283 did not. Therefore, it did not form recently. Therefore, it is old. How old? That is where the argument becomes circular if we are not careful. We cannot derive a precise age from metallicity alone, because the rate of chemical enrichment in the early galaxy is not perfectly known. But we can say something qualitative, and that qualitative statement is powerful. HD 148283 must have formed when the universe was young. Not middle-aged, not mature, young. Within the first billion years or so, when the raw material of stars was still nearly pristine. This is the chemical argument for antiquity, and it is independent of any distance measurement. Even if we didn't know how far away HD 140283 is, even if we had no parallax at all, we would still know, from its spectrum, that it is among the oldest objects in the galaxy. The star wears its age in its chemistry, and there is more. HD 140283 does not simply lack iron. It shows a pattern of elemental abundances that tells a story about the kind of supernovae that enriched the gas from which it formed. The star exhibits what astronomers call alpha element enhancement. Alpha elements, oxygen, magnesium, silicon, calcium, titanium, are produced primarily in the cores of massive stars and ejected in core collapse supernova, the explosive deaths of stars more than 8 times the mass of the Sun. These supernovae happen quickly, within a few million years of the star's birth, and they produce abundant alpha elements but relatively little iron. Iron, by contrast, comes substantially from a different source. Type Ia supernovae, the thermonuclear explosions of white dwarfs in binary systems. These events take longer to occur, hundreds of millions of years, sometimes billions, because the white dwarf must accumulate mass from its companion star before it can detonate. In a young galaxy, where not enough time has passed for many Type Ia supernovae to have occurred, the ratio of alpha elements to iron will be high. In an older galaxy, where Type Ia supernovae have had time to catch up, the ratio will be lower. HD 140283 shows the high alpha to iron ratio characteristic of ancient halo stars. It carries the chemical signature of an era when the galaxy was dominated by core collapse supernovae, when massive stars were living and dying in rapid succession, but the slower Type Ia channel had not yet had time to make its full contribution. This is not just evidence of age, it is evidence of a specific kind of age. The star formed in the first flush of galactic chemical evolution, when the universe was still figuring out how to make iron. Chamberlain and Aller recognized this in 1951, when they published the first spectroscopic confirmation that HD 140283's chemical abundances were lower than the Sun's. They did not have the theoretical framework of nucleosynthesis fully worked out. Fred Hoyle's foundational work on stellar element synthesis would not come until 1954, and the famous B2FH paper that systematized the field would not be published until 1957. But they could see that this star was different. Its spectrum was telling them something about its origin, and they listened. What they heard was the voice of the early universe, because that is what HD 140283 represents. A sample of almost primordial gas, frozen into stellar form and preserved across billions of years. The star is a fossil, not in the biological sense. There are no bones here, no shells, but in the cosmological sense. It is a remnant of an earlier epoch, a piece of the past that has survived into the present. When we study its spectrum, we are studying the chemical composition of the universe as it was when the first galaxies were still assembling, when the Milky Way was a swarm of small protogalactic fragments rather than the grand spiral it would become. This is why metal-poor stars matter. They are time capsules. They preserve information about conditions that existed billions of years ago, information that has been erased from most of the galaxy by subsequent generations of stellar enrichment. The disk of the Milky Way is a palimpsest, written and rewritten by countless cycles of star formation and death. But the halo, that diffuse spherical cloud of ancient stars surrounding the disk, still contains objects that formed in the first chapter of the galaxy's history. HD 16083 is one of them. It is currently passing through the disk on an orbit that carries it high above and far below the galactic plane, but it was not born here. It was born out there, in the halo, in the deep past, and we can read that past in its light. We can measure the abundances of dozens of elements, trace the nucleosynthetic processes that produced them, infer the types of supernovae that contributed to the gas from which the star formed. We can, in effect, do archaeology on the early galaxy using a single star as our primary source. But here is the difficulty. The chemical argument tells us that HD 16083 is old. It does not tell us exactly how old. To translate formed when the universe was young into a specific number of years, we need something more. We need to place the star on the Hertzsprung-Russell diagram. We need to know where it sits in the space of temperature and luminosity, so we can compare it to stellar evolution models and read the age from the position. And that brings us back to distance. The temperature of a star can be measured directly from its spectrum. The colour of the light, the shape of the absorption lines, the relative strengths of different features, all of these encode the surface temperature. For HD 14283, that temperature is roughly 5,150 Kelvin, give or take. It is a yellow star, slightly warmer than the Sun, and this can be determined without knowing the distance at all. But the luminosity is a different matter. We can measure the apparent brightness, the amount of light that reaches our telescopes, but that is a function of both the intrinsic luminosity and the distance. A dim star nearby and a brilliant star far away can look equally bright. To disentangle the two to determine how much energy the star is actually emitting, we must know how far away it is. And here is where the mathematics becomes unforgiving. Luminosity scales as the square of the distance. If you underestimate the distance by 10%, you underestimate the luminosity by roughly 20%. If you overestimate the distance by 10%, you overestimate the luminosity by 20%. The errors propagate, and they propagate non-linearly. On the HR diagram, luminosity determines where the star sits vertically. Temperature determines where it sits horizontally. And the age is read from the position, from the star's location relative to the theoretical tracks that describe how stars evolve over time. For a star like HD 14283, which has exhausted the hydrogen in its core and is now in the subgiant phase, the age is particularly sensitive to the luminosity. A subgiant's luminosity increases as it evolves, as the core contracts and the envelope expands. A slightly more luminous HD 14283 is a slightly more evolved HD 14283, which means it has been burning longer, which means it is older. A slightly less luminous HD 14283 is younger. The relationship is not linear, and it depends on the details of stellar models, on the treatment of convection, on the opacities used, on the assumed helium abundance. But the basic principle is clear. Get the distance wrong and you get the age wrong. And for HD 14283, the age uncertainty we care about is on the order of 1 billion years. We're trying to determine whether this star is 12 billion years old or 14 billion years old or something in between. That 2 billion year range is the difference between a star that fits comfortably within the age of the universe and a star that predates it. A 2 billion year uncertainty sounds enormous in human terms. In cosmological terms, it is a thin margin. The universe is 13.8 billion years old. A star that formed 1 billion years after the Big Bang would be 12.8 billion years old today. A star that formed in the first moments after recombination, as soon as the universe had cooled enough for atoms to form and gravity to begin its work, might be 13.5 billion years old or more. The difference between these scenarios is not a matter of deep eons, it is a matter of the first few percent of cosmic history. And that difference is encoded in the parallax, in the tiny angular shift of HD 1W283 against the background stars as Earth swings around the Sun. Parallax is the foundational method of cosmic distance measurement. It relies on geometry alone, no assumptions about stellar physics, no model dependencies, just the simple fact that a nearby object appears to shift against a distant background when viewed from different positions. Hold your thumb at arm's length and close one eye, then the other. Your thumb appears to jump against the far wall. That is parallax. The universe offers us the same trick, with the Earth's orbit as the baseline and the distant galaxies as the background. For a star like HD 1W283, the parallax angle is tiny. The star lies roughly 200 light-years away, which corresponds to a parallax of about 17 milliseconds. A millisecond is 1,000th of an arcsecond. An arcsecond is 1/60th of an arcminute. An arcminute is 1/60th of a degree. The full moon spans about half a degree or 30 arcminutes or 1800 arcseconds. 17 milliseconds is less than 100,000th the apparent diameter of the moon. Measuring such an angle from the ground is extraordinarily difficult. The Earth's atmosphere shimmers and shifts, blurring stellar images and introducing spurious motions. The practical limit for ground-based trigonometric parallax is around 20 milliseconds, and even at that level the uncertainties are substantial. For a star at HD 140283's distance, the ground-based parallax measurements carried errors large enough to make the derived age essentially useless for addressing the cosmological question. The star might be 14 billion years old. It might be 16 billion years old. The error bars were simply too large to tell. This was the situation for decades. HD 140283 was known to be ancient. The spectroscopy made that clear. It was known to be nearby, as these things go. The proper motion made that clear. But the precise distance, and therefore the precise luminosity, and therefore the precise age, remained frustratingly uncertain. Astronomers could argue about whether the star was older than the universe, but they could not settle the question, because the parallax was not good enough. What changed everything was space. Above the atmosphere there is no shimmering. A telescope in orbit can stare at a star for hours, days, months, building up a precise measurement of its position against the background stars without the constant interference of turbulent air. The images are sharper, the astrometry is cleaner, the parallax can be measured to precisions that would be impossible from the ground. Howard Bond understood this. The astronomer at the Space Telescope Science Institute had been thinking about HD 1828283 for years, puzzling over the age paradox, wondering whether a better distance measurement could resolve it. The Hubble Space Telescope offered a way forward. Its fine guidance sensors, instruments designed primarily for pointing the telescope, for locking onto guide stars and holding them steady, could also be used for precision astrometry. They could measure stellar positions with an accuracy of a fraction of a millisecond. Bond proposed a campaign. Multiple observations of HD 18283 spread over 2 years, capturing the parallax wobble as Earth traced its orbit. The goal was simple: determine the distance to a precision that no ground-based program could match, and use that distance to constrain the age to a precision that might finally answer the question. The observations were carried out between 2003 and 2011. The analysis was painstaking. Every source of systematic error had to be considered. The positions of the reference stars, the geometry of the detector, the small motions introduced by the telescope's own orbital mechanics. When the final parallax emerged, it was 17 or 15 milliarcseconds, with an uncertainty of just 0.2 milliarcseconds. That was an error of less than 1%. It was 5 times more precise than anything the Hipparcos satellite had achieved. From that parallax, Bond's team derived a distance of 58.4 parsecs, about 190 light-years. From the distance, they derived a luminosity. From the luminosity and the temperature, they placed HD 283 on the HR diagram. From the position on the HR diagram, they read the age, and the age was 14.46 billion years, plus or minus 800 million years, accounting for all the uncertainties, the parallax, the temperature, the stellar models. But the central value was clear: older than the universe. The paper landed in 2013 and it made headlines. A star older than everything. Methuselah, the papers called it, reaching for the biblical patriarch who lived 969 years. The name stuck, but the number did not go uncontested. It could not. Either the star was truly older than the cosmos, which would require rewriting cosmology, or something in the measurement chain was wrong. The stakes were too high for the result to stand without challenge, and so the scrutiny began. The parallax itself was re-examined. The temperature was questioned. The stellar models were probed for hidden assumptions. Could there be a systematic error in the fine guidance sensor astrometry? Could the temperature scale be off by 50 Kelvin? 100? Could the helium abundance in the star be different from what the models assumed? Each of these possibilities carried implications. Each offered a way to nudge the age downward, to bring Methuselah back into consistency with the cosmic microwave background. The uncertainty range did, technically, allow for an age as low as 13.66 billion years, just barely younger than the universe. Perhaps the star had formed in the absolute first moments after the Big Bang, as soon as gravity could begin pulling gas together, as soon as the first dark matter halos could collapse and light their first nuclear fires. But just barely consistent is not the same as clearly resolved. The tension remained. The star's most likely age, given the measurements, was still older than its most likely universe, and that meant either the measurements or the models were subtly wrong, in ways that had not yet been identified. What was not in dispute was the star's metallicity. That measurement did not depend on distance. It depended only on the spectrum, on the depth and shape of absorption lines that could be measured directly without any geometric uncertainty. And the spectrum said, clearly and unambiguously, that HD 1483 was extraordinarily metal-poor. 1 part in 200 of the Sun's iron. A star that formed before the galaxy had time to make its metals. A fossil from the deep past, passing through our neighbourhood on an orbit that will carry it away again in a cosmic eye blink. The chemistry and the geometry were both pointing in the same direction. Old. Very old. Old enough to strain the boundaries of cosmology. Old enough to make astronomers uncomfortable. And that discomfort, that tension between what the star seemed to be saying and what the universe would allow, became the engine of a decade's worth of further investigation. The parallax would be remeasured. The temperature would be recalibrated. The stellar models would be refined. The interferometers would be brought to bear, measuring the star's angular diameter directly, providing a new constraint on its radius and luminosity. But all of that lay in the future. In 2013, the number was 14.46 billion years, and the world had to decide what to do with a star that seemed to remember a time before there was time. The question was no longer whether HD 140283 was old. The question was whether our understanding of the universe was complete. And a single point of light in Libra, invisible to the naked eye, crossing the sky at 1,000 kilometers every 3 seconds, had forced that question into the open. But the 2013 paper, dramatic as its conclusions were, did not emerge from a vacuum. The tension it crystallized had been building for years, decades even, and the instruments that made the measurement possible had their own history, their own moment of arrival. To understand why Howard Bond's result landed with such force, we must go back to the satellite that first gave astronomers a truly precise distance to HD 140283. We must go back to Hipparcos. The European Space Agency launched it in August of 1989, a modest spacecraft by the standards of flagship missions, but revolutionary in its purpose. Hipparcos was the first space observatory dedicated entirely to astrometry, to the ancient and painstaking art of measuring where stars are. Not what they are made of, not how hot they burn, not what elements their spectra reveal. Just position, just angle, just the geometry of the sky. The name itself was a kind of homage. Hipparchus of Nicaea, working in the 2nd century BCE, had compiled the first systematic star catalogue in the Western tradition, logging the positions and brightnesses of some 850 stars visible from the island of Rhodes. 21 centuries later, his namesake satellite would do the same work, but from above the atmosphere, with photoelectric detectors instead of human eyes, and with a precision that Hipparchus could not have imagined. the challenge that Hipparchus was built to solve is simple to state and fiendishly difficult to execute. Stars are far away. Their distances are measured through parallax, the apparent shift in a star's position as Earth swings from one side of its orbit to the other. But that shift is tiny. Even for the nearest stars, it amounts to less than 1 arc-second, 1/3600th of a degree. For a star like HD 0283, 200 light-years out, the shift is smaller still, roughly 17 milliseconds, 17 thousandths of an arc-second, a motion so subtle that from Earth's surface, the shimmer of the atmosphere drowns it entirely. Ground-based telescopes had measured parallaxes for over a century, but their precision was limited by the air itself. Turbulence, refraction, the slight bending of starlight as it passed through layers of varying temperature and pressure, all of these conspired to blur the measurements, to introduce noise that could not be averaged away. Hipparchus, orbiting above the atmosphere, would see the stars as points of light, unwavering, their positions tracked with a stability that no ground-based instrument could match. The satellite operated for just over 4 years, from 1989 to 1993, spinning slowly as it swept its twin telescopes across the sky, recording the positions of more than 118,000 stars with a median uncertainty of better than 1 millisecond. When the catalogue was released in 1997, it represented a leap in precision by a factor of 10 or more over the best ground-based work. For the first time, astronomers had reliable distances to thousands of stars that had previously been known only approximately. And among those stars was HD 0283. The Hipparchus parallax for HD 0283 came in at 17.16 milliarc-ekans, with an uncertainty of 0.68 milliarc-seconds. The number itself was unremarkable, close to what earlier estimates had suggested, though now backed by the gold standard of space-based astrometry. But when astronomers fed that distance into their stellar models, combined it with the star's spectrum, its temperature, its luminosity, and traced its position on the Hertzsprung-Russell diagram, the implications were immediate and uncomfortable. The age came out above 14 billion years, not by a small margin, not as a statistical fluctuation that could be dismissed. The Hipparchus distance, combined with stellar isochrones that did not account for the slow settling of helium in a star's interior, implied an age greater than 14 billion years, older than the universe as cosmologists understood it, and unlike earlier estimates, this one came with error bars tight enough to matter. The uncertainty was still substantial, nearly 1 billion years in either direction, but the central value was clear. The star, according to the best data available, was older than everything. Some astronomers had suspected as much for years. HD 140283 had been known as a metal-poor, high-velocity star since the middle of the 20th century. Its chemistry screamed antiquity. Its motion through the galaxy spoke of an origin in the deep halo, far from the disk where younger stars were born. But suspicion is not proof, and before Hipparchus the distance measurements had been too uncertain to pin down the age with any confidence. Now they had a number, and the number was a problem. The late 1990s and the first decade of the new millennium saw a flurry of papers wrestling with the HD 140283 age paradox. Brian Chaboyer at Dartmouth was among those who took the problem most seriously, publishing analyses that explored every avenue by which the age might be reduced. Could the stellar models be wrong? Could the temperature scale be off? Could there be some physical process operating in metal-poor stars that the standard isochrones did not capture? One possibility emerged relatively quickly: helium diffusion. Over billions of years, helium atoms in a star's outer layers slowly sink toward the core, settling under the influence of gravity. This process changes the star's internal structure in subtle ways, altering the rate at which hydrogen burns and shifting the star's position on the HR diagram. Standard isochrones, the theoretical tracks that trace a star's evolution, had not always included this effect. When they were recalculated with helium diffusion taken into account, the implied age of HD 140283 dropped. It came down from above 14 billion years to something closer to 13.5 billion years. But 13.5 billion years was still older than the universe, or at least older than the cosmic age preferred by cosmological models of the time, and the uncertainty remained large, plus or minus 1.5 billion years, a range that stretched from barely consistent with cosmology to wildly incompatible with it. The Hipparcos parallax, precise as it was still the dominant source of error. Until someone could measure the distance more accurately, the age would remain stubbornly uncertain. And so the HD Hwantotio 283 problem entered a kind of limbo. The star was known to be old. It was almost certainly among the oldest stars in the galaxy, a genuine fossil from the earliest epoch of star formation. But whether it was older than the universe itself, whether it represented a true crisis for cosmology, or merely a challenging but ultimately resolvable tension in stellar astrophysics, could not be decided with the data at hand. The astronomical community did what scientists do when faced with an unresolved puzzle. They kept working. They refined their temperature estimates. They improved their models. They waited for better parallaxes, knowing that the next generation of space astrometry missions was already being planned. And they added HD Hwantotio 283 to the short list of benchmark objects, stars whose properties were so extreme, so carefully measured, and so directly connected to fundamental questions that they became touchstones for the entire field. If your stellar model could not reproduce HD Hwantotio 283, your model had a problem. But the star itself was indifferent to the debates it had sparked. It continued on its orbit, falling through the solar neighbourhood at a speed that boggled intuition, a wanderer from the ancient halo making one of its rare passes through the galactic disk. And that orbit, that trajectory, told a story of its own. A biography written not in chemical abundances or parallax angles, but in velocity and direction, in the geometry of a path traced over billions of years. HD Hwantotio 283 is not a disk star. The Sun, by contrast, is. Our home star orbits the galactic centre in a nearly circular path, staying close to the plane of the Milky Way, moving with the general flow of the disk population at a sedate 220 kilometers per second. The stars around us, the ones that make up the familiar constellations, the ones visible to the naked eye on a clear night, are mostly disk stars too, born in the same rotating structure, moving in the same general direction, part of the same gravitational family. HD Hwantotio 283 does not belong to this family. Its motion relative to the Sun is not the gentle drift of a neighbour travelling the same road at a slightly different speed. It is the headlong rush of a traveller from elsewhere, a star on an orbit so different from our own that it seems to belong to a different galaxy entirely, and in a sense it does. The Milky Way, like all large galaxies, did not form in isolation. It grew by accretion, by the gravitational capture and absorption of smaller systems, dwarf galaxies, protogalactic fragments, streams of stars and gas that fell inward over billions of years and were woven into the larger structure. The disk is the product of this assembly, a rotating structure that emerged as gas settled into a plane and formed new generations of stars. But the halo, the vast diffuse cloud of old stars that surrounds the disk and extends far above and below the galactic plane, is different. The halo is the graveyard of the galaxies we consumed. It is populated by the debris of ancient mergers, by stars that were born in other systems and inherited by the Milky Way when their home galaxies were torn apart. HD Hwantotio 283 is one of these. Its orbit is highly eccentric, carrying it from the outer reaches of the halo down through the galactic plane and back out again, a long looping path that takes hundreds of millions of years to complete. Its motion is retrograde. It travels in the opposite direction from the disk's rotation, a signature of an external origin. It did not form in the Milky Way. It formed somewhere else, in a smaller system that no longer exists as an independent entity, and it was accreted into our galaxy's halo when that system was devoured. The most likely candidate for its birthplace is Gaia Enceladus, a substantial dwarf galaxy that merged with the Milky Way somewhere between 8 and 11 billion years ago. The collision was not a single cataclysmic event, but a slow gravitational dance, a drawn-out process during which stars from the smaller galaxy were stripped away and scattered into the Milky Way's halo. The evidence for this merger comes from surveys of stellar velocities and chemical abundances, from mapping the positions and motions of millions of halo stars and finding coherent patterns that reveal their shared origin. HD 140283 fits the profile. Its velocity, its orbit, its extreme metal poverty, all are consistent with an origin in Gaia Enceladus, a star that was already billions of years old when the merger began. And so the star is not merely old, it is a traveller, a refugee, a remnant of a galaxy that no longer exists. It was born in the deep past, in a small system orbiting at the edge of the young Milky Way, and it has been falling through the universe ever since. Its current passage through the solar neighbourhood is a cosmic accident, a brief moment in a trajectory that will carry it back out into the halo, away from the disk, away from us. The numbers are staggering. HD 140283 moves at roughly 360 km per second relative to the Sun. Some estimates place it closer to 800,000 miles per hour. At that speed, it crosses a distance equal to the angular width of the full moon every 1500 years. In human terms, this is almost incomprehensibly fast. In astronomical terms, it is the signature of a halo interloper, a star whose orbit is so elongated that its velocity near perihelion, near its closest approach to the galactic centre, is vastly greater than the placid circular motion of the disk. And yet, for all its speed, the star appears motionless in the sky. The proper motion is just over 1 arcsecond per year, a crawl against the fixed background that would take centuries to become visible to a casual observer. This is the paradox of astronomical scales. A star hurtling through space at hundreds of kilometres every second looks frozen, pinned to the celestial sphere, because the distances are so vast that even at enormous velocities translate into only the slightest angular shifts. What this means, in the context of the age problem, is that HD 140283 carries in its orbit a record of the galaxy's earliest history. It is not simply a point of light with an unusual spectrum, it is a witness. It formed before the Milky Way existed in its current form, before the disk had assembled, before the merger that scattered it into its present orbit. Its chemical poverty speaks of a time when the universe had not yet made its metals. Its trajectory speaks of a time when the galaxy was a chaotic assemblage of small fragments, colliding and merging in the slow gravitational ballet that would eventually produce the spiral structure we see today. To study HD 140283 is to study the biography of the cosmos itself, written in the motion of a single point of light. But biography requires a calendar, and the calendar of the universe is not measured by the orbits of stars. It is measured by light, by the faint glow that fills all of space, the remnant radiation left over from the moment when the cosmos became transparent, when the first atoms formed and the photons that had been trapped in the primordial plasma were finally released to travel freely. It is measured by the cosmic microwave background, and by 2003, humanity had a new and extraordinarily precise map of that ancient light. The Wilkinson Microwave Anisotropy Probe, WMAP, had been launched in June of 2001, sent to a point in space 1 million miles from Earth, where it could scan the sky without interference from our planet's heat or the sun's glare. Its mission was to measure the temperature of the cosmic microwave background with unprecedented precision, to map the tiny fluctuations, the hot spots and cold spots, that encode the conditions of the universe a mere 400,000 years after the Big Bang. On February 11, 2003, the WMAP team announced their first-year results. The map they unveiled was a revelation. It showed the sky as it appeared 13.7 billion years ago, a mottled pattern of temperature variations no larger than 1 part in 100,000, but containing within them the seeds of everything that would follow: the galaxies, the clusters, the vast cosmic web of structure that defines the universe today. From the precise pattern of those fluctuations, cosmologists could extract the fundamental parameters of the cosmos: its geometry, its composition, its rate of expansion, and crucially, its age. The number that emerged was 13.7 billion years, with an uncertainty of only 200 million years. This was not an estimate, it was not a guess. It was the result of fitting the observed fluctuation pattern to theoretical models of the early universe, models that had been tested against decades of independent observations and found to be consistent. The cosmic microwave background, combined with measurements of primordial element abundances and the expansion history traced by distant supernovae, converged on a single coherent picture. A universe 13.7 billion years old, dominated by dark matter and dark energy, expanding from a hot, dense initial state. And then, in March of 2013, the Planck satellite released its first cosmological results. Planck was UPIMAP's successor, launched by the European Space Agency in 2009, equipped with instruments that offered 3 times the angular resolution and 25 times the sensitivity of its predecessor. The map it produced was the most detailed portrait of the cosmic microwave background ever made, and the age it implied was slightly older, 13.82 billion years. The statement from the Planck team was measured but significant. The data revealed, they said, an almost perfect fit to the standard model of cosmology, but with intriguing features that forced a rethinking of some basic assumptions. The universe was older than WMAP had suggested, but only by about 1%. The precision, however, was staggering. The uncertainty on the cosmic age had shrunk to a few tens of millions of years, a fraction of a percent. For practical purposes, cosmologists now knew the age of the universe to within the time it takes a star like the Sun to complete a handful of orbits around the galactic centre. This was the other side of the HD 140283 problem. The star's age, measured through stellar evolution and parallax, came in at 14.46 billion years. The universe's age, measured through the cosmic microwave background and corroborated by independent methods, came in at 13.8 billion years. Both numbers had small error bars. Both were the product of years of careful measurement and modelling, and they did not agree. The stakes were clear. If both measurements were correct, something fundamental was wrong, either with our understanding of stellar physics or with our understanding of cosmology. The tension was not a matter of interpretation or philosophy, it was a matter of arithmetic. 2 different clocks, counting the same span of time, had given different answers, and the discrepancy was not subtle. It was 500 million years, nearly 4% of the total age of the universe, a gap that could not be dismissed as statistical noise. The methods that had produced the cosmic age were, by 2013, among the most robust in all of physics. The cosmic microwave background measurement alone would have been compelling, but it did not stand alone. It was supported by Big Bang nucleosynthesis, the theory that predicts the primordial abundances of light elements based on the temperature and density of the universe in its first few minutes. The observed ratios of hydrogen to deuterium to helium, measured in ancient gas clouds and the oldest stars, matched the predictions of the standard cosmological model with remarkable accuracy. And the expansion history of the universe, traced by the redshifts and apparent brightnesses of Tapaya supernovae, provided yet another independent constraint. This was the work that had won Saul Perlmutter, Brian Schmidt, and Adam Rees the 2011 Nobel Prize in Physics. The discovery that the universe's expansion is accelerating, driven by a mysterious dark energy that makes up roughly 70% of the cosmic energy budget. All 3 methods, as the microwave background, nucleosynthesis, and supernovae, pointed to the same age. They used different physics, different observations, different systematic uncertainties, and yet they converged. This is the hallmark of robust science. Independent lines of evidence, subject to different biases, arriving at the same conclusion. The age of the universe was not a single fragile measurement. It was a consensus, a hard-won intersection of multiple approaches, each reinforcing the others. And HD 140283, sitting quietly in Libra, appeared to violate it. The documentary register shifts here from measurement to meaning. On one side of the ledger, a single star, its light gathered by telescopes, its distance measured through parallax, its age inferred from the position it occupies on a theoretical diagram. On the other side, the universe itself, its age encoded in the faint glow that fills all of space, in the ratios of primordial elements, in the redshifts of distant explosions. Both sides of the ledger are the product of human ingenuity, of instruments built and theories refined over generations, and both sides seem to be telling the truth, even though the truths they tell are incompatible. This is the nature of a genuine scientific tension. It is not a failure of knowledge, it is the frontier of knowledge, the place where our understanding ends and the unknown begins. The astronomers who studied HD 140283 in the years after the Planck results knew that they were working at this frontier. They knew that the age paradox could not be resolved by casual adjustment or wishful thinking. Something, somewhere, was wrong. Either the stellar models or the cosmic models or the measurements themselves contained an error that had not yet been found. And finding that error, or failing that, accepting the possibility of new physics, was the task that lay ahead. For now, the star continued on its orbit, indifferent to the calculations it had inspired. It had already been falling through the galaxy for billions of years before the first humans looked up at the night sky. It would continue falling long after the last telescope was shuttered. Its trajectory carried it through epochs that human civilization would never witness, through a future as incomprehensibly long as its past. And somewhere in that trajectory, in the geometry of its orbit and the chemistry of its atmosphere, and the precise shade of light that left its surface and travelled 200 years to reach our instruments, there was an answer. There was a resolution to the paradox, a way to reconcile the age of the star with the age of the universe, to bring both sides of the ledger into agreement. The search for that resolution would drive the next decade of research. It would take astronomers to the limits of what could be measured, to the deepest refinements of stellar physics, to the subtle interplay of observation and theory that defines the practice of astrophysics at its best. And it all began with a single uncomfortable fact, a star that seemed to remember a time before there was time. The search began not with a telescope, but with a proposal. In astronomy, as in so much of modern science, the hardest part is often the waiting for telescope time, the waiting for the right conditions, the waiting for the committees to meet, for the referees to respond, for the schedules to align. Howard Bond knew this rhythm intimately. He had spent decades in the quiet bureaucracy of observational astronomy, navigating the peculiar economy of access that governs who gets to point the world's most powerful instruments at which patch of sky, and for how long. And by the early 2000s he had become convinced that the Methuselah problem could not be solved without better data, and that better data required the Hubble Space Telescope. Bond was an astronomer at Pennsylvania State University, though his career had taken him through the corridors of the Space Telescope Science Institute in Baltimore, the nerve centre of Hubble operations, where proposals arrived by the thousands and only a fraction were approved. He understood what it took to compete for time on an oversubscribed instrument. He understood that every hour granted to his project was an hour denied to someone else's, to the study of distant galaxies or exoplanet atmospheres, or the violent deaths of massive stars. The telescope's schedule was a zero-sum game, and the currency was scientific merit. To win time, you had to convince a panel of your peers that your question mattered more than the alternatives, that your methods were sound, that your target was the right one. And for HD Wolstein 0283, Bond believed he could make that case. The hypothesis was straightforward. The apparent age paradox might stem from inaccurate distance measurements. Everything else in the age calculation, the temperature, the metallicity, the luminosity class, depended on knowing how far away the star actually was. If the distance was wrong, then the luminosity was wrong, and if the luminosity was wrong, the position on the Hertzsprung-Russell diagram was wrong, and if the position on the diagram was wrong, the age was wrong. The entire chain of inference rested on a single geometric measurement, the parallax. Hipparchos had provided a parallax for HD 140283, but the uncertainty was substantial. The mission had measured the star's annual wobble at 17.16 milliseconds, plus or minus 0.68 milliseconds. That error bar, nearly 4% of the measurement itself, translated directly into uncertainty in the distance, and from there into uncertainty in the luminosity and age. The central estimate suggested an age older than the universe, but the error bars were large enough that, strictly speaking, the result was compatible with younger ages. The paradox was suggestive, not definitive. It hovered at the edge of significance, frustrating and unresolved. Bond believed that Hubble could do better. The telescope's fine guidance sensors, originally designed to lock onto guide stars and hold the telescope steady during long exposures, had proven themselves capable of measuring stellar positions with extraordinary precision. Other astronomers had used them to pin down the distances to Cepheid variables, to calibrate the cosmic distance ladder, to resolve binary star orbits. The instruments could achieve millisecond accuracy under the right conditions, and for a star as bright as HD 140283, those conditions were favourable. What was needed was not a single snapshot, but a sustained campaign. Multiple observations spread across years, time to catch the star at the extremes of its apparent motion, when the parallax signature was strongest. The geometry of parallax dictates the observing strategy. As Earth orbits the Sun, a nearby star appears to shift against the background of more distant objects, tracing a tiny ellipse over the course of a year. The amplitude of that ellipse is the parallax angle, and it is largest when Earth is at opposite ends of its orbit, roughly 6 months apart. To measure the parallax with maximum precision, you want to observe the star when it is at one extreme of its apparent position, then again when it is at the other extreme, and you want to repeat this process over multiple years to beat down the statistical noise and identify any systematic effects. Each observation adds to the dataset. Each dataset constrains the model a little more tightly. It is the accumulation of measurements, not any single observation, that produces the final answer. Bond and his collaborators designed their program around this rhythm. They requested observations at 11 separate epochs, spread across nearly 8 years, from August 2003 to March 2011. Each epoch was scheduled near a biannual maximum of the parallax factor, when the geometric leverage was greatest. The spacing was not arbitrary. It reflected the mechanics of orbital motion and the statistics of error reduction. More observations meant smaller uncertainties, but only if the observations were properly distributed. Cluster them too tightly and you lose the baseline. Space them too widely and you risk instrumental changes, calibration drifts, the slow accumulation of systematic errors that plague any long-term measurement campaign. The scheduling was a compromise, a balance between ideal geometry and practical constraints. And then there was the calibration problem. Measuring an absolute position on the sky is fiendishly difficult. What you actually measure in most astrometric work is the position of your target relative to other stars in the same field. The reference stars, which are assumed to be so distant that their own parallax is negligible. But those reference stars are not perfect. They have their own motions, their own distances, their own small parallaxes that must be accounted for. They may drift relative to each other due to subtle optical effects in the instrument. They may be contaminated by background galaxies masquerading as point sources. To extract the true parallax of HD Saturn 0283, Bond's team had to understand the positions and motions of every reference star in the field, to model the systematic errors of the fine guidance sensors themselves, to correct for the slight distortions introduced by Hubble's optics. The measurement was not a simple subtraction. It was a painstaking reconstruction, a fitting of models to data, a triangulation in the most literal sense. The proposal went through the usual channels. It was reviewed, critiqued, revised, resubmitted. It competed against hundreds of other proposals, each claiming urgency, each promising scientific return. The panels met, the scores were assigned, the allocations were made, and eventually the time was granted, not all at once, but incrementally, year by year, as the program demonstrated its value and the data accumulated. This is how large observational campaigns proceed, not with a single dramatic moment of approval, but with a grinding, iterative process of justification and renewal, a perpetual negotiation with the gatekeepers of telescope time. The first observations came in August 2003. The fine guidance sensors locked onto HD while Tholskius 283 measured its position relative to the background stars, recorded the data, and transmitted it back to Earth. Then the telescope moved on to other targets, other programs, other priorities. 6 months later, the star was observed again, and again, and again. Year after year, the data points accumulated, a sparse but precious time series, each measurement adding a little more weight to the final parallax determination. This is the unglamorous reality of precision astrometry. There are no sudden breakthroughs, no eureka moments in the data. There is only the slow, patient accumulation of evidence, the gradual tightening of the error bars, the incremental march towards significance. For nearly 8 years, Bond and his collaborators watched the data arrive, processed it, calibrated it, fit it to their models. They watched the uncertainty shrink, they watched the parallax estimate converge, and they waited for the moment when they could say, with confidence, that they had measured the distance to HD 14283 more precisely than anyone before. That moment came in 2013, when the team published their results. The final parallax was 17.15 milliarc seconds, plus or minus 0.14 milliarc seconds. The central value was almost identical to what Hippocos had found, but the error bar was 5 times smaller, 5 times more precise. That single improvement, that reduction in uncertainty by a factor of 5, transformed the nature of the problem. What had been a suggestive anomaly became a sharp constraint. What had been a vague discomfort became a genuine tension. Bond himself explained the logic in plain terms. One of the uncertainties with the age of HD 3 was the precise distance of the star, he said. It was important to get this right because we can better determine its luminosity, and from that its age. We were looking for the parallax effect. With the refined parallax in hand, the team recalculated the star's luminosity, placed it on the Hertzsprung-Russell diagram with new precision, and derived an updated age estimate. 14.46 billion years, plus or minus 0.31 billion years. The central value was still older than the universe, but now, with the smaller error bars, the star's age was within acceptable uncertainty of the cosmic age of 13.8 billion years. The lower end of the stellar age range, around 14 to 15 billion years, overlapped with the upper end of the cosmic age range, around 13.84 billion years. The tension was not resolved, but it was softened. The paradox remained, but it had become a question of subtle discrepancies rather than outright contradiction. This was the fruit of 8 years of careful work. Not a revolution, not a dramatic overturning of previous results, but a refinement, a sharpening of the blade. The Hubble campaign had not made the paradox go away. What it had done was measure it with unprecedented precision, forcing astronomers to take it seriously as a constraint on their models rather than dismissing it as measurement noise. The star that seemed to remember a time before time was still, by the best available reckoning, uncomfortably old. But now, at least, the discomfort was quantified. And yet the parallax, for all its importance, was only one part of the story. The age of a star is not written solely in its distance. It is written in its light, in the detailed spectrum of radiation that pours from its surface and carries, encoded in the wavelengths of absorption and emission, the chemical history of its birth cloud. To understand when HD 283 formed, astronomers had to read that chemical record with the same care they had brought to measuring its position. The instruments capable of such reading are scattered across the world's great observatories. At the summit of Mauna Kea in Hawaii, the twin Keck telescopes carry the high-resolution Echelle spectrometer, HIRES, an instrument designed to disperse starlight into its component wavelengths with exquisite precision. In the Atacama Desert of Chile, the Very Large Telescope hosts UVES, the ultraviolet and visual Echelle spectrograph, a similarly powerful instrument capable of dissecting the spectra of faint ancient stars. These spectrographs are the forensic tools of stellar archaeology. They reveal not just what elements are present in a star's atmosphere, but in what proportions, and from those proportions astronomers can infer the history of the gas cloud from which the star condensed. For HD 283, the chemical verdict was unambiguous. This was a star born in the earliest epoch of galactic history. Its iron content was roughly a factor of 250 lower than the Sun's, a staggering deficit that placed it firmly among the most metal-poor stars known. But the story was more nuanced than simple poverty. The ratios of different elements revealed a characteristic signature, one that pointed to the specific processes that had enriched its birth cloud before the star itself formed. Population 2 stars, the ancient metal-poor stars of the galactic halo, typically show an elevated ratio of alpha process elements relative to iron. Alpha elements are those whose nuclei are built from integer multiples of helium nuclei: oxygen, neon, magnesium, silicon, sulfur, calcium, titanium. These elements are forged in the cores of massive stars and ejected into the interstellar medium when those stars explode as Type II, like supernovae. The core collapse explosions that mark the deaths of stars at least 8 times more massive than the Sun. Type II supernovae are fast. A massive star lives only a few million years before exhausting its fuel and collapsing. The elements it produces are scattered into space almost immediately on cosmological timescales. They are the first heavy elements to appear in the universe, the first contributions to the chemical enrichment of pristine hydrogen and helium. Iron, by contrast, has a more complicated origin. While some iron is produced in Type II supernovae, the majority comes from Type Ia supernovae, the thermonuclear explosions of white dwarf stars in binary systems. These explosions take longer to occur. A white dwarf must first form from the death of a lower mass star, then accrete material from a companion until it reaches a critical mass. The process takes hundreds of millions to billions of years. By the time Type Ia supernovae begin to contribute significantly to the interstellar medium, the universe is already old enough for multiple generations of stars to have lived and died. The chemical signature of HD Softone-O-83 reflects this timing. Its atmosphere shows the fingerprint of Type II enrichment, the elevated alpha to iron ratio that indicates it formed before the Type Ia supernovae had time to flood the galaxy with iron. Its birth cloud was assembled in the very first burst of nucleosynthesis, when massive stars were the only source of heavy elements, when the cosmos was still young enough that slow processes had not yet had time to act. The spectrum of the star is a fossil record of that primordial epoch, a chemical snapshot of conditions that prevailed in the first few 100 million years after the Big Bang. But the chemistry of HD 10283 contains another puzzle, one that deepens rather than resolves the mystery of its origins. This puzzle concerns lithium, the lightest metal, the third element in the periodic table, and one of the few elements created in significant quantities during the Big Bang itself. In the standard model of Big Bang nucleosynthesis, the intense heat and density of the early universe forged hydrogen, helium, and trace amounts of lithium in the first few minutes after the initial expansion. The predicted abundance of primordial lithium, specifically the isotope lithium-7, can be calculated from first principles using the same physics that correctly predicts the abundances of hydrogen and helium, and for decades, astronomers expected to find this primordial abundance preserved in the atmospheres of the oldest, most metal-poor stars, stars so ancient that they formed before subsequent generations of stellar nucleosynthesis had a chance to alter the cosmic lithium budget. The expectation was confirmed, at least partially, by the work of Francois and Monique Speet, who in the early 1980s measured the lithium abundances of a sample of hot, metal-poor stars. They found a striking pattern. Regardless of metallicity, these stars all showed approximately the same lithium abundance, a flat distribution that came to be known as the Spite Plateau. This uniformity was exactly what you would expect if the stars were all preserving the same primordial value, the lithium forged in the Big Bang and carried, unchanged, through billions of years. But there was a problem. When the GeoMap satellite measured the cosmic microwave background with unprecedented precision in the early 2000s, it allowed cosmologists to recalculate the expected primordial lithium abundance using updated values for the baryon density of the universe. The revised prediction was approximately 2.6 dex, a logarithmic unit of abundance, and this theoretical value was a factor of 2 to 3 higher than the lithium abundance actually observed on the Spite Plateau. The stars had too little lithium. The Big Bang, according to the standard model, should have produced more. This discrepancy, known as the cosmological lithium problem, remains one of the outstanding puzzles in modern astrophysics. It is not a small effect. A factor of 2 to 3 is not a rounding error. It is a genuine mismatch between theory and observation, one that resists easy explanation. Some theorists have proposed that lithium is destroyed inside stars, processed in ways that current models do not fully capture. Others have suggested that the standard model of Big Bang nucleosynthesis itself might need revision, that there is new physics at work in the early universe that alters the primordial lithium yield. Neither explanation has gained universal acceptance. The lithium problem persists, an unresolved tension running parallel to the age paradox, and HD 140283 sits at the intersection of both puzzles. Unlike many metal-poor stars, it has a detectable amount of lithium in its atmosphere, a consequence of its evolutionary state. The star has not yet evolved into a red giant, the phase of stellar life when convection dredges up material from deep interior layers and can destroy surface lithium. Its lithium abundance is preserved, or at least less altered, making it a crucial benchmark for understanding chemical evolution in the early Milky Way. But that lithium abundance, like the abundances observed in other Spite Plateau stars, is lower than the Big Bang prediction. HD 140283 participates in the lithium problem even as it defines the age paradox. The two mysteries are layered inside each other, each one complicating the interpretation of the other. A star that appears older than the universe also preserves a chemical signature that contradicts the standard model of cosmic nucleosynthesis. The more closely astronomers examine Methuselah, the more anomalies they find. What does this tell us? At the very least, it tells us that HD 140283 is not simply an isolated curiosity. Its peculiarities are connected to some of the deepest questions in cosmology and stellar physics, questions that touch on the age and composition of the universe itself. The star's chemistry confirms what its motion and metallicity already suggested. This is an object that formed at the very edge of cosmic history, in the brief window between the recombination of the primordial plasma and the onset of sustained star formation. Its atoms were assembled from the debris of the first supernovae, the explosions of stars that themselves had formed from pristine Big Bang material. It is a second-generation star at most, perhaps among the very first objects that could reasonably be called a star in the modern sense. And yet, for all its antiquity, it is here. It is 200 light-years away, close enough to be studied in exquisite detail, close enough for Hubble to measure its parallax and for Keck and the VLT to dissect its spectrum. It is a neighbour, in cosmic terms, a relic of the ancient universe that happens, by some accident of orbital mechanics, to be passing through our corner of the galaxy at this particular moment in cosmic time. Its presence in our sky is a gift, a stroke of luck that allows astronomers to probe conditions that would otherwise be accessible only through the faintest, most distant observations. The spectroscopic record of HD 140283 is, in this sense, a kind of time capsule. Every absorption line in its spectrum, every subtle shift in wavelength, every ratio of one element to another, carries information about the state of the universe when the star was born. The alpha element enhancement speaks of Type II supernovae, of massive stars that lived fast and died young, of a cosmos still too young for the slow processes of stellar evolution to have made their mark. The lithium abundance speaks of the Big Bang itself, or rather, of the puzzling gap between what the Big Bang should have produced and what we actually observe. The iron deficiency speaks of a time before iron was common, before billions of years of Type Ia supernovae had seeded the galaxy with the element that would one day form the cores of rocky planets. To read the spectrum of HD 140283 is to read the autobiography of the early universe, written in the language of atomic physics and encoded in the wavelengths of light. It is a document that predates everything we would recognize as familiar, every galaxy, every planet, every organic molecule. The photons that carry this information have travelled only 200 years to reach our instruments, but the information they carry is nearly 14 billion years old. We are decoding a message sent before the Milky Way existed in its current form, before the Sun was born, before the Earth condensed from the disk of gas and dust that would become our solar system. And the message, for all its richness, is incomplete. The chemistry tells us when the star formed, within broad limits, but it cannot tell us exactly how old it is. For that, we need the parallax, the distance, the placement on the Hertzsprung-Russell diagram, the comparison with theoretical models of stellar evolution. We need the full apparatus of modern astrophysics, applied with all the care and precision that Bond and his collaborators brought to their 8-year Hubble campaign. We need the slow, patient accumulation of data, the grinding refinement of error bars, the incremental approach to truth that characterizes science at its best. And even then, even with all of that, we may not arrive at a definitive answer. The age of HD 140283 depends on models as well as measurements, and models can be wrong. The stellar evolution codes that place the star on the Hertzsprung-Russell diagram make assumptions about convection, about opacity, about the mixing of elements in stellar interiors, assumptions that are tested against observation but never perfectly verified. The cosmic age derived from the microwave background depends on the cosmological model, on the assumed values of parameters like the Hubble constant and the dark energy equation of state, parameters that are themselves the subject of ongoing debate. Both sides of the ledger, the stellar and the cosmic, rest on theoretical foundations that are robust but not unassailable. This is the nature of the enterprise. Science does not offer certainties. It offers best current estimates, subject to revision as new data arrive and new models are developed. The age paradox of HD 140283 is not a failure of the scientific method. It is the scientific method in action. It is the tension between observation and theory that drives progress, that forces astronomers to question their assumptions, that ultimately leads to deeper understanding. The star that seems to remember a time before time is not an embarrassment. It is an opportunity, a chance to probe the limits of our knowledge and perhaps, to discover something genuinely new about the universe we inhabit. For now, the star continues on its long fall through the galaxy, carrying its ancient chemistry and its anomalous age across the void. It has already travelled farther than human comprehension can easily grasp. It will continue travelling long after every telescope currently in operation has fallen silent. Its journey is indifferent to our curiosity, indifferent to our models, indifferent to the paradoxes it creates for the creatures who, for a brief moment in cosmic time, have learned to read its light. But we have learned, and what we have learned, painstakingly assembled from parallax measurements and spectroscopic analyses and theoretical models, is that this star is a messenger from the edge of time. Its presence in our sky is a reminder that the universe is older than we sometimes imagine, and stranger and more resistant to simple summary. It carries, in the wavelengths of its light, questions that we are only beginning to know how to ask. The search for answers continues. The search for answers continues, but the path forward leads not outward into the cosmos, but inward, into the heart of the theoretical machinery that translates raw observation into age. Because here is the uncomfortable truth that every astronomer working on HD 140283 understands but rarely says aloud to a general audience. The number 1446 billion years is not a direct measurement, it is an inference. It is what you get when you take a parallax, convert it to a distance, use that distance to calculate a luminosity, plot that luminosity against a temperature on a Hertzsprung-Russell diagram, and then ask a computer model to tell you how old a star must be to occupy that particular point in the diagram. The parallax is measured, the temperature is measured, but the age is computed and the computation depends on assumptions about how stars work. Assumptions that are sophisticated, physically motivated, tested against countless observations, but assumptions nonetheless. The models in question are called stellar evolution codes, and they are among the most complex pieces of software in all of astrophysics. They attempt to simulate the entire life of a star, from its initial collapse out of a cloud of gas to its eventual death as a white dwarf, neutron star or black hole. They track the flow of energy from the nuclear furnace at the core to the radiating surface. They account for the gradual conversion of hydrogen to helium and then to heavier elements as the star ages. They model the convective currents that stir the stellar interior, carrying heat from deep regions to shallow ones. They include the effects of radiation pressure, of electron degeneracy, of magnetic fields, of mass loss through stellar winds. They are, in a sense, attempts to encode the physics of a star into a set of differential equations that a computer can solve, and they are not all the same. Different research groups have developed different stellar evolution codes over the decades, each with its own philosophy, its own implementation choices, its own calibration against observed stars. The BASTI models, developed by a consortium of Italian and Spanish astronomers, take one approach. The Dartmouth Stellar Evolution Program, known as DSEP, takes another. The Victoria Regina models, developed at the University of Victoria in British Columbia, represent a third tradition. GARSTEC, PARSEC, the Yale-Yonsei isochrones. Each of these is a distinct attempt to capture the physics of stellar evolution in computational form, and each produces slightly different results when fed the same input data. For most stars, the differences are small enough to ignore. The models agree on the broad outlines of stellar evolution, on the main sequence lifetimes of solar-type stars, on the way red giants expand and cool as they exhaust their core hydrogen. But HD 144683 is not most stars. It sits in a region of the Hertzsprung-Russell diagram where the models are sensitive to their internal assumptions, where small changes in the input physics can produce large changes in the inferred age. It is a subgiant, meaning it has exhausted the hydrogen in its core and is beginning to expand and cool, but it has not yet reached the red giant branch. This evolutionary phase is brief, a few 100 million years out of a lifetime measured in billions, and the exact position of a star in this phase depends critically on details that are difficult to model from first principles. Consider convection. In the outer layers of a star like HD 144283, energy is transported not by radiation, but by the physical motion of hot gas rising and cool gas sinking, like a pot of water on a stove. This convective motion determines how efficiently the star radiates energy, which in turn affects its surface temperature and luminosity. But modelling convection in 3 dimensions, with all its turbulent complexity, is computationally prohibitive. Instead, Stellar evolution codes use an approximation called mixing length theory, which treats convection as a one-dimensional process characterized by a single parameter, the mixing length, typically expressed as a multiple of the pressure scale height in the stellar atmosphere. This parameter is calibrated by requiring the model to reproduce the observed properties of the Sun, but there is no guarantee that the solar calibration applies to a metal-poor halo star with a completely different chemical composition. Different choices of the mixing length parameter can shift the inferred age of HD 10283 by several hundred million years. Or consider the initial helium abundance. When a star forms, it inherits a certain fraction of helium from the gas cloud that gave it birth. This helium fraction affects the star's structure, its luminosity, and its evolutionary timescale. For the Sun, the initial helium abundance can be inferred from heliosismology, the study of sound waves propagating through the solar interior. But no such diagnostic is available for distant stars. For HD 10283, the initial helium abundance must be assumed, and different assumptions lead to different ages. A higher initial helium fraction makes the star brighter at a given evolutionary stage, which means it must be older to have reached its current luminosity. A lower helium fraction has the opposite effect. The uncertainty is not arbitrary. There are physical constraints on how much helium could have been present in the gas from which HD 10283 formed, but within those constraints there is room for disagreement, and then there is atomic diffusion. Over the billions of years of a star's life, heavy elements and helium gradually settle toward the core under the influence of gravity, while hydrogen floats upward. This slow segregation changes the composition of the outer layers, affecting the star's opacity and temperature. It also changes the composition of the core, affecting the rate of nuclear reactions. Modelling this process requires tracking the diffusion of each element separately, accounting for the competing effects of gravity, radiation pressure, and turbulent mixing. Different codes handle diffusion differently, and the differences matter. Including helium diffusion in the models for HD 10283 can reduce the inferred age by several hundred million years, bringing it closer to the cosmic limit. The cumulative effect of these uncertainties is sobering. When Bond and his collaborators published their 2013 result, they quoted an age of 14.46 billion years with an uncertainty of plus or minus 0.31 billion years. But that uncertainty reflected only the observational errors, the precision of the parallax, the accuracy of the spectroscopic temperature, the reliability of the photometric data. It did not include the systematic uncertainties inherent in the stellar models themselves. When those model uncertainties are included, the error bar expands dramatically. Different model grids, fed the same observational inputs, produce ages that range from about 12 billion years to more than 15 billion years. The spread is larger than the observational error. It is larger than the discrepancy between the star's nominal age and the age of the universe. The models themselves are the dominant source of uncertainty. This is not a failure of the models. It is a reflection of the genuine physical complexity of stellar interiors, combined with the impossibility of directly observing what happens inside a star. The models are not arbitrary. They are constrained by decades of observation, by the requirement that they reproduce the properties of stars we can study in detail, by the fundamental laws of physics. But they contain parameters that must be calibrated rather than derived, and those parameters have room to vary. Within the space of physically plausible assumptions, the age of HD 10283 can be pushed above or below the cosmic deadline. The paradox is not resolved. It is dissolved into a fog of uncertainty. For an audience accustomed to the precision of modern astronomy, the microwave background measured to 4 significant figures, the Hubble constant determined to within a few percent, the masses of exoplanets weighed with remarkable accuracy. This may come as a surprise. Surely we know how stars work. Surely we can trust the models. But the truth is that stellar astrophysics, for all its sophistication, retains pockets of genuine ignorance. The interiors of stars are among the most hostile environments in the universe, inaccessible to direct observation, knowable only through the light that emerges from the surface and the theoretical frameworks we construct to interpret that light. The frameworks are powerful, but they are not perfect. The uncertainties they carry are real. And so the question becomes, which uncertainty breaks first? Is the star younger than it appears because some assumption in the models is wrong? Or is the universe older than we think because some assumption in the cosmological models is wrong? Or is the distance still slightly in error, despite the unprecedented precision of the Hubble observations? Each possibility has defenders. None has been conclusively eliminated. In March of 2013, the tension became public. Bond and his collaborators published their results in the Astrophysical Journal Letters, one of the premier venues for announcing significant astronomical discoveries. The paper was titled HD 14283, a star in the solar neighbourhood that formed shortly after the Big Bang, and it laid out the case with meticulous care. The parallax was 17 or 15 plus or minus 0.14 milliarcseconds, a factor of 5 more precise than the Hipparcos measurement. The corresponding distance was 58.30 plus or minus 0.48 parsecs, or about 190 light-years. The luminosity calculated from the apparent brightness and the distance was approximately 5 times that of the Sun. The temperature measured from the spectrum was about 5,150 Kelvin, nearly identical to the Sun's, but placed at a different point on the Hertzsprung-Russell diagram because of the star's higher luminosity. And the age, derived by comparing this position to theoretical isochrones, was 14.46 billion years. The uncertainty quoted in the paper was 0.31 billion years for the formal error, and 0.8 billion years when systematic uncertainties were included. This meant that the star could, in principle, be as young as 13.66 billion years, younger than the universe's 1382 billion years, but only barely. The overlap was real, but it required every source of error to break in the same direction simultaneously. The probability of that happening by chance was low. The most likely age, the central value of the estimate, remained stubbornly older than the cosmos itself. The paper was careful not to claim a paradox outright. The authors noted the tension, acknowledged the uncertainties, and called for further investigation. But the media needed no such caution. Headlines around the world announced the discovery of a star older than the universe. The story was irresistible. A cosmic, impossible object, hiding in plain sight just 190 light-years from Earth, challenging everything we thought we knew about the age of creation. HD 14283 acquired its nickname in the popular press, Methuselah, after the biblical patriarch who lived 969 years, the oldest man in Scripture, the star that outlived the universe. The scientific community's response was more measured but no less intense. The result was not dismissed as an error. The Hubble observations were too careful for that. Instead, it was treated as a frontier, a place where current understanding was being tested and found wanting. The question was not whether to believe the measurement, but how to interpret it. Something was wrong somewhere in the chain of reasoning that connected the parallax to the age. The task was to find it. The logical structure of the problem was clear. The age estimate depended on 3 inputs: the distance, the stellar parameters derived from spectroscopy, and the theoretical models. The distance was now as precise as ground-based parallax could make it. Hubble's fine guidance sensors had pushed the error down to less than 1%. Further improvement would require waiting for Gaia, the European Space Agency's astrometric satellite, which was still years from launch. The spectroscopic parameters, temperature, surface gravity, chemical abundances, were well determined, though some refinement was possible. That left the models. In the years following the 2013 publication, several research groups took up the challenge of reconciling HD 14283 with the cosmic age. The most systematic effort came from Don Vandenberg at the University of Victoria, a leading expert on stellar evolution models for old, metal-poor stars. Vandenberg and his collaborators examined the assumptions underlying the isochrone fits, looking for places where defensible changes in the physics could reduce the inferred age. They found several. The most significant involved the oxygen abundance. HD 14283 is extremely iron-poor, with an iron content roughly 250 times lower than the Sun's. But its oxygen content, relative to iron, is enhanced, a signature of enrichment by Type II supernovae in the early universe. This oxygen enhancement affects the star's internal opacity, which in turn affects its structure and evolution. When Vandenberg's team recalculated the age using updated oxygen abundances, They found a value of 14.27 billion years, plus or minus 0.38 billion years. Still older than the universe, but slightly less so. The direction was encouraging, even if the magnitude was insufficient. Other groups explored other adjustments. The treatment of helium diffusion was refined, with more sophisticated models tracking the settling of helium into the core over cosmic time. The mixing length parameter was re-examined, with some researchers arguing that a smaller value might be appropriate for metal-poor stars. The equation of state, the relationship between pressure, temperature and density in the stellar interior, was updated to reflect improved laboratory measurements of atomic properties. Each change nudged the age downward, by a few 100 million years here, a few 100 million there. By 2014, some estimates had fallen to around 13.7 billion years, still older than most cosmological determinations, but within the zone of plausible overlap. But the most dramatic revision came nearly a decade later. In 2021 and 2022, a series of papers appeared that combined new observational techniques with updated stellar models to push the age estimate lower still. The key innovation was astroseismology, the study of oscillations in the stellar surface, analogous to the sound waves that probe the interior of the Sun. For HD 140283, direct astroseismic measurements were not available, but careful analysis of the star's observed properties, combined with interferometric measurements of its angular diameter from the Cara array, allowed researchers to constrain its fundamental parameters more tightly than ever before. The result, published in 2022, was startling: an age of 12.0 plus or minus 0.5 billion years. This was not just consistent with the age of the universe, it was comfortably younger, with room to spare. The revision came not from a single dramatic discovery, but from a systematic tightening of every link in the chain. Better angular diameters, better calibrations, better treatment of systematic effects in the models. The star that had seemed impossibly old was now merely ancient. Yet the controversy did not end. Other researchers, using different models and different analysis techniques, continued to find ages in the 13 to 14 billion year range. An astroseismic analysis yielded 14.2 plus or minus 0.4 billion years, older again. The spread in published ages, from 12 billion to more than 14 billion years, reflected the genuine difficulty of the problem, the sensitivity of the result to assumptions that remained debatable. No consensus emerged. The paradox was not resolved. It was merely bounded, constrained to a range of possibilities that included both conflict with and compatibility with the cosmic age, depending on which set of assumptions you trusted. And what of the cosmic age itself? Could that side of the equation be adjusted? The answer in principle is yes. The age of the universe derived from the cosmic microwave background depends on the cosmological model, on the values of parameters like the Hubble constant, the matter density, and the dark energy equation of state. If any of these parameters were different from the currently accepted values, the inferred age would change. The Hubble constant is particularly relevant. This number, denoted h0, measures the rate at which the universe is expanding, the velocity at which distant galaxies recede from us per unit distance. A higher Hubble constant means a faster expansion, which in turn means a younger universe. Less time has elapsed since the Big Bang. A lower Hubble constant means a slower expansion and an older universe. The current best estimate from the Planck satellite based on the cosmic microwave background is about 67 km per second per megaparsec. But measurements based on local distance indicators, Cepheid variables, type Ia supernovae, tend to give higher values, around 73 km per second per megaparsec. This discrepancy, known as the Hubble tension, is one of the most actively debated problems in cosmology. If the lower value is correct, the universe is about 13.8 billion years old. If the higher value is correct, the universe is closer to 12.5 billion years old, younger, and the HD 1.283 paradox becomes even more severe. But some theoretical models propose a Hubble constant lower than 67, which would make the universe older than 13.8 billion years and ease the tension with the star's age. These models typically invoke non-standard dark energy, with an equation of state that differs from the simple cosmological constant assumed in the standard model. Such modifications are speculative, and none has gained wide acceptance. but they remain on the table as logical possibilities, part of the landscape of potential resolutions. The dark energy equation of state is another knob that could, in principle, be turned. In the standard cosmological model, dark energy is described by a cosmological constant, with an equation of state parameter W equal to exactly -1. This means that dark energy has a constant density, unchanging as the universe expands. But if W differs from -1, if dark energy's properties evolve over time, the expansion history of the universe changes, and so does the inferred age. Measurements of W are consistent with -1, but the uncertainties are large enough to permit small deviations. A value of W slightly less than -1 would make the universe older. A value slightly greater would make it younger. The precision required to distinguish these cases is at the frontier of current observational capability. None of these cosmological adjustments is required by the HD 4283 data alone. The simplest interpretation remains that the star's age, properly calculated with appropriate model uncertainties, is consistent with the cosmic age. Old, certainly among the oldest stars in the galaxy, but not impossible. The paradox in this view is an artifact of underestimated systematic errors, now being corrected through better observations and better theory. The universe is 13.8 billion years old. The star is 12 or 13 billion years old. There is no contradiction. But this tidy resolution depends on trusting the most recent analyses over the earlier ones, on believing that the 2022 age estimate of 12 billion years is more reliable than the 2013 estimate of 14.46 billion years, and that trust is not universal. Some researchers continue to argue that the older age estimates were correct, that the revisions have introduced new systematic errors as they corrected old ones. The debate is technical, involving detailed discussions of stellar atmospheres, convective overshooting, atomic diffusion coefficients, matters far removed from the public narrative of a star older than the universe, but essential to resolving the underlying science. This is what it looks like when a paradox is examined rather than resolved. The tools of astronomy have been brought to bear on HD 4283 with unprecedented precision. Parallaxes measured to fractions of a millisecond, temperatures determined to tens of Kelvin, chemical abundances catalogued element by element. The theoretical machinery of stellar evolution has been refined, updated, recalibrated against new observations. The cosmological parameters have been measured with exquisite accuracy, cross-checked by multiple independent methods, and yet the question remains open. The star's age is uncertain by more than 1 billion years, a span of time longer than the existence of complex life on Earth, longer than the entire Phanerozoic eon, longer than anything in human experience can meaningfully grasp. Within that uncertainty lies either a confirmation of our understanding or a hint of something we have not yet imagined. The response to this uncertainty is not despair, it is iteration. Each new measurement, each refinement of the models, each theoretical insight narrows the range of possibilities, even if it does not eliminate the tension entirely. The parallax from Gaia, the European astrometric satellite launched in 2013 and still operating, provides an independent check on the Hubble distance. The astroseismic techniques developed for nearby stars will, in time, be applied to metal-poor halo objects. The stellar evolution codes will continue to improve as computational power increases and our understanding of stellar physics deepens. The cosmological parameters will be measured with ever greater precision by future surveys of the microwave background, future observations of supernovae, future maps of the large-scale structure of the universe. Science responds to a paradox not with a shrug but with a research program. The star that seems too old is not an embarrassment to be hidden, but a target to be studied. Its very existence, its stubborn refusal to fit neatly into our models, is what makes it valuable. It is a test case, a stress test for the entire framework of stellar and cosmological physics. Every attempt to reconcile its age with the age of the universe teaches us something, whether the attempt succeeds or fails. The learning is in the trying, and so the measurements continue, the models are refined, the uncertainty narrows slowly, incrementally, with all the patience that science demands. HD 4283 remains in its eccentric orbit, falling through the galaxy on a trajectory older than most of the stars it passes. It carries no awareness of the paradox it poses, no concern for the debates it has sparked. It is simply an ancient star, doing what ancient stars do, fusing hydrogen in its core, radiating light into the void, tracing a path through space that it has followed for longer than the Earth has existed. The questions belong to us. The answers, when they come, will come from the slow accumulation of evidence, the patient testing of hypotheses, the willingness to follow the data wherever it leads. For now, the data lead to a tension that has not been fully resolved, a star whose age remains debatable, a universe whose history may yet hold surprises. The parallax is precise, the chemistry is ancient, the models are sophisticated, and the question persists. How can this star, burning steadily in the constellation Libra, seem to remember a time before there was time? The search for answers continues, and the next chapter of the search will take us from the star itself to the broader context in which it exists, the cosmological framework that gives meaning to the phrase age of the universe, and the growing evidence that even that framework may harbour tensions of its own. The framework itself, it turns out, is under siege. Through the late 2010s and into the 2020s, as HD 42283 continued its quiet transit through the constellation Libra, a separate crisis was sharpening in the offices and observatories where cosmologists work. It had nothing to do with ancient stars, at least not directly. It concerned something far more fundamental, the rate at which the universe is expanding, a number called the Hubble constant, and the deeply troubling fact that two independent methods of measuring it were refusing to agree. The disagreement is not subtle. It is not the kind of discrepancy that can be waved away as instrument noise or calibration drift. One set of measurements, derived from the cosmic microwave background radiation observed by the Planck satellite, yields a Hubble constant of approximately 67 km per second per megaparsec. Another set, derived from observations of Cepheid variable stars and type Ia supernovae in the local universe, yields approximately 73. The difference, 5 to 6 km per second per megaparsec, may sound small in absolute terms, but it is far larger than the quoted uncertainties on either measurement. Both methods have been refined to extraordinary precision. Both are internally consistent, and yet they disagree, persistently and stubbornly, in a way that has come to be known as the Hubble tension. The implications cut to the core of cosmology itself. If the Hubble constant is on the lower end, closer to 67, then the universe is expanding more slowly than the local measurements suggest, and the age of the universe extends upward toward 14 billion years or beyond. In that scenario, HD 140283's estimated age becomes unremarkable. The star would simply be old as the cosmos allows, but not paradoxically so. But if the Hubble constant is on the higher end, closer to 73, then the universe is younger, perhaps only 12.5 billion years old, and the tension with Methuselah does not merely persist, it worsens. An ancient star in a young universe is more than a puzzle, it is an impossibility. Adam Rees, the Johns Hopkins astronomer who shared the 2011 Nobel Prize for the discovery of dark energy, has spent years refining the local measurement. He leads the SHIAS collaboration, Supernova H0, for the equation of state of dark energy, and has pushed the Cepheid calibrated supernova method to its limits. The Carnegie-Chicago Hubble program, an independent effort, has reached similar conclusions using slightly different techniques. Both find values clustered around 73, with uncertainties now small enough that the disagreement with Planck cannot be dismissed as statistical fluctuation. Hubble would be amazed, Rees remarked, to see that we are still using Cepheids. The method pioneered nearly a century ago remains central to the measurement, though the instruments and analysis techniques have advanced beyond anything Edwin Hubble could have imagined. The tension sharpened as both sides improved their precision. In the early years, skeptics suggested that the discrepancy would vanish once systematics were better understood, that the Cepheid measurements were somehow biased, or that the Planck data harboured unrecognised errors. But as the decade wore on, the error bars shrank and the disagreement remained. The James Webb Space Telescope, launched in late 2021 and delivering its first science data in 2022, offered a new test. Its infrared vision could observe Cepheids with unprecedented clarity, cutting through the dust that might have biased earlier measurements. The result, a Hubble constant of 72.6 km per second per megaparsec, nearly identical to the value Hubble had found for the same galaxies. The local measurement held firm. The tension was not an artifact of old instruments or poor calibration. It was real. And here is where HD 140283, that quiet magnitude 7 object in Libra, becomes something more than an isolated curiosity. The star is never mentioned in the hundreds of papers that have been written about the Hubble tension. It is not a player in the debates between the SURE-ES team and the Planck collaboration, not a variable in the complex statistical analyses that attempt to reconcile the two measurements, but it stands at the intersection of two independent crises, a silent witness to a conflict that now occupies some of the best minds in physics. If the universe is older than the standard model suggests, if the true Hubble constant is closer to 67, then the paradox of the star dissolves. If the universe is younger, if the local measurements are correct, then the paradox deepens into something that cannot be explained by measurement error alone. Either way, the star's apparent age is not merely a problem for stellar astrophysics, it is a data point in a much larger argument about the structure of the cosmos itself. The proposed resolutions to the Hubble tension read like a catalogue of exotic physics. Early dark energy, a burst of accelerated expansion in the first few 100,000 years after the Big Bang, could change the sound horizon that Planck uses to calibrate its measurement. Additional relativistic species, particles beyond the known families of neutrinos that were present in the early universe, could alter the expansion history in subtle ways. Modified gravity, departures from Einstein's general relativity on cosmological scales, might reconcile the observations without requiring new particles at all. Each proposal carries consequences, rippling through the interlocking equations that describe the universe's evolution from the Big Bang to the present day. And each proposal, if true, would change the context in which HD 140283's age is interpreted. The star, of course, knows nothing of these debates. It continues on its trajectory, indifferent to the theoretical crises its existence has helped to sharpen. But for those who study the universe's history, the star has become a kind of boundary marker, a physical object whose properties constrain what theories are permissible. It is not enough for a cosmological model to explain the microwave background and the supernova data. It must also allow for the existence of a star that formed in the first billion years after the Big Bang and survived to the present day. Any model that yields a universe younger than HD 3's minimum plausible age is ruled out by the star's mere presence in the sky. The physics must accommodate the fact. This is what it means for a star to be a load-bearing puzzle piece in the structure of cosmology. HD 140283 is not an anomaly to be explained away. It is a constraint, a boundary condition that any successful theory must satisfy. The tension between its age and the universe's age is not a failure of astronomy, but a signal, a place where our models touch the real world and find friction. That friction is productive. It tells us where to look for missing physics, where our assumptions might be incomplete, where the next breakthrough might lie. The star's existence, awkward and difficult to reconcile, is precisely what makes it valuable. And so the debates continue in journals and conference halls and the quiet hours of computation that fill an astronomer's working life. The Hubble tension is not resolved. The star's age is not nailed down to a single definitive value. The uncertainty persists, and with it the possibility that something fundamental about our understanding remains to be discovered. This is the state of play as the third decade of the 21st century unfolds. A universe whose expansion rate refuses to be pinned down, a star whose formation date hovers at the edge of the permissible, and a scientific community that has responded not with frustration, but with intensified effort. The measurements will improve, the models will be tested. The truth, whatever it turns out to be, will eventually yield to the slow pressure of accumulated evidence. But there is another dimension to this story, one that transcends the technical debates and reaches towards something more immediate. HD 140283 is not just a data point. It is a physical object, a ball of hydrogen and helium some 200 light-years away, tracing a path through the galaxy that brings it from time to time into our neighbourhood. The star is falling. That is perhaps the simplest way to describe its motion. It is falling through the disk of the Milky Way, plunging downward from the ancient halo of stars that surrounds our galaxy like a sparse and lonely shroud. Its velocity is enormous, approximately 800,000 miles per hour relative to the Sun, and its trajectory is eccentric, nothing like the nearly circular orbits of the younger metal-rich stars that populate the disk. It is a visitor from the deep past, passing through our region of the galaxy on its way to somewhere else. In roughly 1.5 million years, HD 1683 will pass within about 40 light-years of the Sun. 40 light-years is still an immense distance by human standards, roughly 10 times the distance to Alpha Centauri, but by galactic standards, it is practically next door. The star will be closer to us than it has been in billions of years, a temporary neighbour in the vast emptiness of interstellar space. Then it will continue on its arc, swinging outward and upward, returning to the halo from which it came. It will not stay. It is passing through, as it has passed through countless times before, on an orbit that it has traced for longer than the Sun has existed. To call it a neighbour feels almost presumptuous. This is not a star that belongs to our community of disk-dwelling objects. It is an interloper from a different era, a relic of a galaxy that no longer exists in its original form. The evidence suggests that HD 130283 was born not in the Milky Way itself, but in a primeval dwarf galaxy, a small, metal pore system that formed in the early universe and was later gravitationally shredded and absorbed by our own galaxy. That merger, if it occurred, happened more than 12 billion years ago. The dwarf galaxy is gone, its stars scattered throughout the Milky Way's halo, indistinguishable now from the native population, except by their chemistry and their orbits. HD 130283 is one of these orphans, a survivor of a structure that was ancient when the Sun was not yet a possibility. The materials from which it formed were themselves the products of even more ancient processes. In the first few 100 million years after the Big Bang, the universe contained no elements heavier than lithium, hydrogen, helium, a trace of lithium, that was all. The first stars, the population 3 objects that theorists have modelled but never directly observed, formed from this pristine gas. They were massive, hundreds of times the mass of the Sun, and they burned hot and fast. Their lives lasted only a few million years, eye blinks in cosmic time, before they exploded as supernovae, scattering the first heavy elements into the surrounding void. Carbon, oxygen, iron, all the elements that would eventually build planets and life. They were forged in those first stars and dispersed by their deaths. HD 130283 formed from gas that had been seeded by those explosions. Its extreme metal poverty, iron roughly 250 times less abundant than in the Sun, tells us that the enrichment was minimal, that only a handful of those first supernovae had contributed their debris to the cloud from which the star coalesced. Everything that made HD 140283 was already ancient by the standards of the universe, a mere billion years or so after the Big Bang. The star has been burning steadily ever since, converting hydrogen to helium in its core, slowly evolving along the sequence that all stars follow. It has outlasted the dwarf galaxy in which it was born. It has outlasted most of the structures that existed when it formed. It has witnessed, in some sense, that admits no consciousness, the entire history of cosmic structure formation, the assembly of galaxies, the rise and fall of stellar generations, the emergence of planets and, on at least one of them, creatures capable of looking back. And here, perhaps, is where the documentary must pause before its close. We have followed the measurements and the models, the parallaxes and the spectra, the tensions and the debates. We have traced the star's orbit and its chemistry, its origin in the deep past and its future trajectory through the galaxy. But there is something that remains after all the analysis is complete, something that persists beyond the error bars and the theoretical frameworks. It is the simple, irreducible fact of the star's existence. HD 140283 is real. It is not a theoretical construct or a statistical abstraction. It is a physical object, a point of light in the constellation Libra, visible on any clear night to anyone with a pair of binoculars and a star chart. Its apparent magnitude of 7205 places it just below the threshold of naked eye visibility, but only just. A dark sky and patience will bring it within reach. It is there, burning, radiating, tracing its ancient path through the galaxy, whether or not anyone observes it. To look at it is to look at something that may genuinely predate our ability to fully account for it. the age estimates conflict: 14.46 billion years in one study, 12 billion in another, somewhere between 12 and 14 billion in the most recent analyses. The error bars are real. The tension is real. The uncertainty is not a failure of measurement, but an honest acknowledgement of the limits of our knowledge. We do not know with certainty exactly when this star formed. We know only that it formed very early, in the first billion years of cosmic history, and that it has survived to the present day. That survival is itself remarkable. Most stars that formed when HD 42283 formed are long dead. Their matter recycled into new generations of stars and planets. This one persists, a survivor against all odds, still fusing hydrogen, still radiating light, still falling through the galaxy on its ancient orbit. The paradox in the end may not be a paradox at all. It may simply be a measure of our current ignorance, a gap in our understanding that future measurements and theories will eventually close, or it may be a genuine clue to something we have not yet discovered, a hint of new physics lurking at the intersection of stellar evolution and cosmology. Either way, the star has done what a good scientific puzzle should do. It has forced us to examine our assumptions, test our models, and confront the limits of what we know. The tension between the star's age and the universe's age is not a scandal or an embarrassment. It is a research program, a set of questions that will drive observations and theory for years to come. Howard Bond, the astronomer who led the Hubble campaign that brought HD Versteinzone 283 to widespread attention, put it plainly. Maybe the cosmology is wrong, he said. Stellar physics is wrong, or the star's distance is wrong. Those three possibilities remain in play. The distance, measured with exquisite precision by Hubble and now by Gaia, is probably not wrong by enough to resolve the tension. The stellar physics is under continuous scrutiny, with each new model refining our understanding of how stars age. The cosmology, the framework that tells us the universe is 13.8 billion years old, is itself under pressure from the Hubble tension and may yet require revision. The answer, when it comes, will come from the patient accumulation of evidence, the willingness to follow the data wherever they lead, and the intellectual honesty to admit uncertainty where uncertainty exists. And so we end where we began, with a star. Not a concept, not an equation, but a physical object, burning in the night sky, carrying in its spectrum and its motion the record of an unimaginably distant past. HD 140283, Methuselah, the star that seems to remember a time before there was time. It asks nothing of us. It makes no claims. It simply exists, as it has existed for longer than the sun, longer than the Earth, longer than the Milky Way in its current form. It is an artifact of near-nothingness, forged from gas that was barely touched by the first stellar explosions, drifting through a galaxy that has changed beyond recognition since the star was born. To observe it is an act of connection across time. The light that enters a telescope tonight left the star roughly 200 years ago, when the Industrial Revolution was transforming human society. But the star itself has been there, burning, for perhaps 14 billion years, or 12, or something in between. The uncertainty, frustrating as it may be to those who seek definitive answers, is part of the story. It is the honest acknowledgement that we are still learning, still measuring, still refining our understanding of a universe that is under no obligation to make itself easy to comprehend. The error bars are real, the tension is real, and the star is real, a magnitude 7 object in Libra, an ancient halo wanderer on a trajectory that will bring it closer to us in 1,000,000 years before it swings back into the dark. Find it if you can. Point your binoculars at the coordinates, wait for the sky to darken, and let the light fall on your retina. You will be looking at something older than almost everything else you can see, a survivor of the universe's earliest epoch, a witness to a history that stretches back to within a heartbeat of the beginning. What you make of that is up to you, but the star will be there regardless. Burning, drifting, enduring. It was there before the questions were asked, and it will be there long after the answers, whatever they turn out to be, have been found. That persistence, that quiet endurance, is perhaps the most remarkable thing of all. In a universe defined by change, by the relentless cycles of stellar birth and death, one ancient star continues on its way, carrying the signature of a time so distant that our models strain to account for it. That is not a failure of science. It is its most luminous kind of success, the discovery of something so old, so strange, so difficult to explain, that it forces us to think harder, measure more carefully, and admit how much we do not yet know. The mystery of HD 54283 is not a door closed. It is a door opened to new physics, perhaps, or to deeper understanding of the physics we already have. Either way, the search continues, and the star burns on, as it has burned for all the ages of the world and more. A neighbour who remembers, a wanderer who was old before the sun was born, a light in Libra, waiting to be seen.